Hello everyone. So in this video, I'm going to cover electric potential and capacitance. So first we'll go through the syllabus and I'll cover all concepts, all derivations and problems that can be asked in your board exams. Now this is the detailed syllabus. So we'll be covering electric potential, then the potential difference and electric potential by a point charge, by a dipole and by a system of point charges, then the concept of equipotential surfaces, and then the electric potential energy of a system of 2-point charges, and the potential energy of an electric dipole placed in external electric field. Then the concept of conductor, and then dielectrics, what happens to the dielectric in electric field, then capacitors, and what is then the capacitance, and the combination of capacitors in a series and parallel network, and then what happens to the capacitance if we place a dielectric between the plates, and then what is the capacitance formula for capacitance for a parallel plate capacitor with or without dielectric, and then the energy stored in the capacitor. And here in the syllabus it is clearly mentioned, you don't have to know the derivation for the energy stored in the capacitor, only formula is required. So first concept that we have to study is electric potential. So definition is given here, so let us understand. So let us say we have a charge capital Q placed here, it is fixed, and we want to find what is the electric potential at point P. Like we have studied electric field in the last video. So electric field will be having different values at different points from the charge. Similarly, we can define a scalar quantity which is known as electric potential, and it will be having different values at different points in space with respect to the charge Q. Now, if I bring a unit positive charge, let us say Q is the charge, and we are bringing this charge from infinity to this point P. And let us say the work done by the external agent will be W external from infinity to point P. So if this is our charge Q, and let us say it is at certain distance from capital Q, so it will experience a repulsion in the right direction. Now this is the electric field in right direction. And due to this electric field, it will experience a force QE in the right direction. So if I want to bring this charge very slowly in the field of capital Q, we have to apply a force in the opposite direction. Now this is the external force. Now this external force has to be nearly equals to the electrostatic force, so that the kinetic energy of Q will not change, or we can say it will be nearly remain zero, right? So the work done by the external agent will be positive because the force we are exerting force in the left direction and the displacement is also in the left direction. But the work done by the electric force is negative because electric field is in the right direction, or the force on the charged particle is in the right direction and displacement is in the left direction. So what we can say, work done by external agent will be negative of the work done by electric field from infinity to P. Or what I can write this as minus work done by electric field, or simply I can say it will be plus work done by electric field from P to infinity. So if we find the work done by electric field from P to infinity, we can find the potential at P. So let us see. So potential at P is defined as work done by external agent from bringing the charge from infinity to point P very slowly, divided by Q, where Q is the charge on the particle which we are moving in the field. And this can be written as work done by electric field from P to infinity divided by Q. Right. So when this charged particle is at a distance r from capital Q, let us say there is a small displacement dr in the right direction. So what is the small amount of work done? So small amount of work done by the electric field can be written as F dot dr, or I can write this as Q times E dot dr. So if I integrate this, we will get the integrate this from, let us say this distance is capital R, and obviously Q is this is at infinity, right? So from capital R to infinity, so R to infinity, right? So this can be written as integral R to infinity QE dot dr divided by q. Since q is constant, so we can eliminate q in the numerator and denominator, and we will get integral r to infinity e dot dr, right? Now, what is the electric field by a point charge? So we have studied in the last video, it will be kq by r square. So I can write this as an electric field and dr both are in the same direction. So this can be written as integral r to infinity kq by r square dr. And the integration of 1 by r square is minus 1 by r. So kq will come out of the integration and we have minus 1 by r, and the limit is from r to infinity. So if we substitute the limits, we'll get kq times minus 1 by infinity plus 1 by r. So this comes out to be k capital Q by r. Now this is the potential at point P by a point charge. So you have to remember this formula. So Vp is kq by r, right? And this is the general formula. If you want to find the potential at a point P, so first we have to find the work done bringing a charge from infinity to that point very slowly. Okay, right. So we know both the formulas which were given here. So V is W by Q, and the dimensional formula of potential is this, and this you can quite easily find out by using dimension analysis. Okay, right. Now let us see the next concept. When we have more than one charges, then what we can do? Electric potential is a scalar quantity. So what are you going to do? You'll find the potential by one charge and you can simply add them. So for example, if we have a charge Q, say this is Q1, this is Q2, right? And this is Q3, and there are many charges, and this is Qn. And let us say we want to find the potential at P. So if we know these distances, let us this is R1, this is R2, and this is R3, and say this is Rn. So we can find potential by individual charges and simply add them, right? So this is the formula for potential at point P by multiple charges. Now, what is electric potential difference? Let us understand that. In the last section, we have seen potential at point A will be work done by the external agent in bringing charge, unit positive charge from infinity to point P or point A divided by the charge, right, which we are moving. Now, so this is the potential at A. Let me show you. Let us this point is B and this point is A, and we are bringing charge Q from infinity, right? So potential at A is given by this formula. Similarly, potential at B will be given by work done by the external field from infinity to B divided by Q, right? So we can say in one case, we are displacing charge Q up to this distance. In the second case, we are displacing charge Q up to this distance. So what extra work that we have to do? So we have to do extra work for this particular displacement. So what we can say, potential difference between B and A will be work done by the external agent in bringing the charge Q from A to B divided by Q. Got it? And this work done by the external agent, this can be written as negative of work done by the electric field from A to B by Q. Is it clear? And this can be written as integral Q E dot dr from A to B divided by Q. So this Q will get eliminated. So VB minus VA will be minus integral E dot dr from A to B. So this is the relation between the potential difference between A and B, right? So this is a relation between electric field and the potential difference. So do remember this relation. It is very important relation. If electric field is given to you, by using this relation, we can find potential difference between 2 points. So in this problem, we have given a point charge Q, plus Q is placed at point O as shown in the figure. Is the potential difference VA minus VB positive, negative or zero? So we know what is the potential by a point charge at a particular distance. So we know V at A will be KQ by, let us say this is RA. Similarly, potential at B will be KQ by RB. Since RA is less than RB, we can say VA will be greater than VB because V and R are inversely related. So with the potential at A is greater than potential at B, so VA minus VB will be positive, right? Okay. So, and one thing you can also figure out from here, as we are going in the direction of the electric field, the potential decreases because the potential at A is greater than the potential at B. Now let us see the next question. Figure shows the field lines on a positive charge. Is the work done by the field in moving a small positive charge from Q to P positive or negative? Work done by the field, right? From Q to P. So we want to move the charge from Q to P, and we know that the electric field is in this direction and the charge is positive. So this is the direction of force, this is the displacement. So force and displacement are opposite to each other, so we can say work done will be negative. So negative is the answer. Now the next question, what is the amount of work done in moving a point charge around a circular arc of radius r at the center of which another point charge is located? So we have given a charge q and we want to move another charge on this circular path. So this radius is r. So at any 2 points, so if I consider any point, let us say there is a charge q which is moving in this circular path, and we want to move this charge on this circular path. So what is the work done? So at every point on this circular path, the potential will be K capital Q by R. Since the potential is not changing and we know the relation, V is W by Q, or you can say it will be delta V will be the total work done by the external agent divided by Q. So work external will be Q times delta V. So if you know potential between the 2 points, we can find the work done by the external agent moving that a point charge between those 2 points. So here there is no change in the potential, so work done will be 0. So the answer will be 0. Right, now let us see the next question. A 500 microcoulomb charge at the center of a square of side 10 centimeters. So we have given a square of side 10 centimeter, right? So this, and 500 microcoulomb charge is placed at the center. Find the work done in moving a charge of 10 millicoulomb between two diagonally opposite points. Suppose we want to move a charge of 10 millicoulomb from say A to C. So what is the potential at A? We can say it will be 500 microcoulomb times K divided by half of the diagonal. Let us say D is the diagonal, so half the diagonal. So what is the potential at C? Again, it will be same, right? 500 micro K divided by D by 2. Since potential at A and potential at C are same, and so work done by the external agent in moving a charge of 10 millicoulomb from A to C will be 10 milli times the change in potential. So VC minus VA, and VC and VA are equal, so it comes out to be 0. So the answer will be 0. Right. Now let us see another question. So draw a plot showing the variation of electric field and the electric potential with distance r from the point charge. In the last video, we have seen electric field by a point charge will be kq by r square, and today we have seen potential is kq by r. Right? So if I plot electric field and potential on the same graph, when r is 1, both will be having same value, right? When R is 1, both will be having same value, KQ and KQ. So I'm showing potential with V with red color and the electric field with the black color. If R is, let us say 2, right? If R is 2, in that case electric field will become KQ by 4 and V will become KQ by 2. So potential will be greater. In magnitude, potential will be greater for R equals to 2. So we can say if this is 2, if this is potential, electric field will be electric field will be a bit lower than that, right? And similarly, if I put R as say zero point 0.5, if R is 0.5, then electric field will be KQ by 4 KQ, right? And potential will be 2 KQ. So electric field will be more for 0.5, right? If this is the electric field, then potential will be less than that, right? Now if I plot the graph, we know that as R increases, potential and electric field both decreases. So let me show you the graph. So this is the graph for the potential, and if I show the graph for the electric field, it will be something like this. Right? So this is for electric field and the red one is for potential. So do remember this graph. It has been asked multiple times. Right. Now let us see the next question. So 2 point charges Q and minus 2Q are kept d distance apart. Find the location of the point relative to charge small q at which the potential due to this system of charges is 0. Right. So we have given small q and minus 2q, small q at d distance apart. And we want to find the position where the electric potential by this system is 0. Right. So if I take a point, say P, right? So let us say P. P is a point at which the potential is 0. So to make the potential 0, charge Q will be having positive potential and negative charge will be having negative potential. So we know that the potential formula is KQ by R. Now this Q we have to put with proper sign. If it is a negatively charged particle, then the potential will be negative. If it is a positively charged particle, then the potential will be positive. So at this point, the algebraic sum will comes out to be 0. So if this distance is x, so this distance will be d minus x. So we can say at P, the potential is 0. So it will be KQ by x minus K2Q by d minus x. So let us simplify this. So this KQ will get eliminated. So we have 1 by x should be equals to 2 by d minus x. So d minus x is equals to 2x and x comes out to be d by 3. So at a distance d by 3 from small q, the potential will be 0. Right. So now let us see one more question. So 2 point charges 4 microcoulomb and minus 2 microcoulomb are separated by a distance 1 meter in air. Calculate at what point on the line joining the two charges is the electric potential 0. Again, it is the same question, right? So I'm keeping this for you to solve on your own because we have covered the same concept. Right. Now let us see the electric potential by a dipole. So we are going to cover like three important two positions, equatorial and axial position. Like we have calculated electric field for axial position and the equatorial position. So first I'm going to cover axial position. So this is minus q and this is plus q and the distance between the two charges is 2L. and we want to find the potential at point P. And here I'm taking an assumption that R, which is the distance of point P from the center of the dipole, is very large in comparison to 2L, right? Length of the dipole. So potential at P will be what? So now we have two charges, so we have to find the potential by both the charges, simply add them. So due to negative charge, it will be minus kq upon R plus L, and due to positive charge, it will be kq upon R minus L. So let us simplify this. So kq will come out, and we have minus 1 by R plus L plus 1 upon R minus L. Let us simplify this. So it will be kq minus R plus L plus R plus L divided by R square minus L square. Now this R will get eliminated. So we can say it will be kq 2kq times L divided by R square minus L square. Now this is the general formula. And if we apply this assumption, then we can say R square minus L square will be nearly equals to R square, because L is very small in comparison to R. So this comes out to be, and 2qL is nothing but the electric dipole moment. So it will be pk divided by R square, right? So that is the potential due to a dipole at a point on the axis. Now the second case is equatorial position. So this is a positive charge, this is negative, and we want to find the potential at point P. Now if you look at this problem, the P point will lie on the perpendicular bisector. So we can say P is equidistant from plus Q and minus Q. If it is equidistant, then the magnitude of the potential by both the charges will be same, but they have opposite sign. So potential at P comes out to be 0, right? Now let me take the, cover one more case, that is the general case. So this is negative charge and this is positive charge, and electric dipole moment is in this direction, and we want to find the potential at point P, which is at a distance r from the center of the dipole. And I'm taking this angle as theta, and let us take it as a position vector, right? So r is the position vector of point P from the center of the dipole. And we know that electric dipole is a vector quantity. Let us resolve this vector in two mutually perpendicular directions. So this component will be P cos theta, and this component will be P sin theta. Now point P with respect to P cos theta is on the axial position, and with respect to P sin theta, P point is at the equatorial position. So due to P sin theta, there will be no contribution towards electric potential. So we are left with P cos theta, and we know that at the axis, the potential is Pk by R square. So we have to replace P with P cos theta. So potential will become Kp cos theta divided by R square. Now if I want to write this in vector notation, unit vector notation, no, not unit vector, in vector notation, so I can write this as, if I multiply numerator and denominator with R, so this will become K P dot R divided by R cube, or I can also write this as K P dot R cap divided by R square. So if you know position vector, if you know R vector in unit vector notation and P in unit vector notation, you can directly apply the dot product and you can find the potential at that point. I hope this concept is clear to you. Right. So the next concept is the potential by a shell. If we have a uniformly charged shell, what is the potential? So let us understand that. So shell is given, it has a charge, let us say Q. And we want to find, so you can say there are three important points. One will a point which is inside the shell, one point on the surface of the shell, and the third point will be outside the shell. So if I consider a point outside, let us say point A. So what is the potential at A? So by definition of electric potential, to find the potential at A, we need to move a charge Q from infinity to point A, and then we'll have to calculate the work done by the external agent and divide that work done by the charge Q. We'll get the potential at A. Now we are going to apply the same concept. So the nature of the field outside the shell is same as the field by a point charge. So we can say potential at A will be nothing but KQ by R, right? This is R because field is same. So if I do the same working, I'll get the same answer. So potential at A will be KQ by R. Similarly, the potential at point B will be KQ by capital R, because at B the distance of B from the center is capital R, which is where R is the radius of the shell. Now if I want to find the potential at C, so we can say it will be, so potential at C will be work done from infinity in bringing a charge Q from infinity to point C by Q, or I can write this as work done from infinity to point B plus work done from B to C, right? By Q. And we know that work done from infinity to B upon Q is nothing but the potential at B, right? And from B to C, we know that there is no electric field inside the shell. If there is no electric field, there will be no change in the potential, because VB minus VA is minus integral E dot dr, where integration is from A to B. So if electric field is 0, VB minus VA becomes 0 if E is 0. So we can say this will be 0 and this will be nothing but potential at B. So potential at C is same as the potential at B, or you can say at any point on the surface or at any point inside the shell, the potential will be same and it is equals to the potential on the surface. So potential inside is same as potential on surface, and this will be KQ by capital R. I hope this concept is clear to you. Right. So, and if we have a non-conducting solid sphere, this portion is not in your board syllabus. So just it is not required to do this, right? So just remember the formula. If we have a solid sphere with which is non-conducting, it is having uniform volume charge density. Let us the total charge is Q. Outside, the potential will be same as the potential by a point charge concentrated at the center of the sphere. So here the potential will be KQ by small r. At the surface, it will be KQ by capital R. Inside point, you can say it will be KQ by R cube, 1.5 R square minus 0.5 small r square, where small r is the distance of that point from the center. No need to remember this because it will not ask, it not been asked in your board exams. Just remember these two values, right? So the next concept is equipotential surface. It is a surface at which the potential does not change. Let me give you an example of that. Let us say there is a positive charge, and if I join all points which are equidistant from this point charge, so at every point on this surface, the potential will be KQ by R, where R is the distance from the point charge. So it is an equipotential surface. Now let us see some important properties of equipotential surface. So the first property is electric field lines are always perpendicular to this. So if I show field line for this point charge, it is radially outward. So at every wherever this field line is intersecting this equipotential surface, you can clearly see that they are orthogonal to each other. They are perpendicular, right, everywhere. And the second important property is if we move up a point charge on this surface, it will the work done will be 0. Yes, we know the formula, right? What is the work done by the external agent in moving a charge from one point to another? It will be Q times the difference in potential, right? V final minus V initial. And in this case, for equipotential surface, both these potentials are same, so it comes out to be 0. Now the third point is that two equipotential surface never intersect each other. So if electric field is perpendicular to the equipotential surface, if there are two equipotential surface, then we can say at the point of intersection, if this is surface 1, the field will be normal to this, and due to the surface 2, the field will be normal to this. So at a given point, we are getting two different directions of electric field, which is not possible. So you have to keep these 3 points in your mind. Now let us see a typical question that can be asked from equipotential surfaces where you have to draw the equipotential surface. So let us see the question. So draw equipotential surface due to point Q, positive charge. Are these surfaces equidistant from each other? If no, explain why. Let us see. So if you draw the equipotential surface by this point charge, we can say I've shown three equipotential surface. Let us say this surface has a potential 100 volt and this surface has a potential 80 and this has a potential 60 volts. So as we are going in the radially outward direction, the potential decreases by 20 volt if we move from one equipotential surface to the another equipotential surface. And the gap between 80 and 60 is more than the gap between 100 and 80. Why this gap is there? So we know that the change difference in the potential will be minus E times dr, where dr is the displacement in the direction of electric field. So potential decreases in the direction of electric field. So in this case, I have kept the difference between two consecutive equipotential surfaces as 20. So it means I have fixed this value. So it has fixed to 20, right? So minus 20. So if this is fixed, and we know that as we go away from the point charge, the electric field decreases. So as electric field decreases, we can say this dr should increase, right? So that's why the gap between the second and the third equipotential surface is more than the gap between first and the second. I hope the justification is clear to you. Now let us see the next question. So 2 point charges, 2 microcoulomb and minus 2 microcoulomb are placed at a points A and B 6 centimeters apart. Draw equipotential surface of the system. And why do the equipotential surface gets closer to each other near the point charge? Okay, so if you draw the electric field line, so we have a dipole basically, right? So if you draw electric field line, so this is the pattern of electric field line. They will originate from the positive and terminate on the negatively charged particle. So like this. And we know that the equipotential surface will be perpendicular to the electric field. So if you look at any surface, so at every point, wherever this equipotential surface intersect with the electric field and the surface will be perpendicular to each other at every point, right? So like this, we can draw the equipotential surface for this positive charge and similarly for the negative charge. Now the second part says, why do the equipotential surface gets closer to each other near the point charge? So again, we're going to apply the same concept that the change in potential will be minus E times dr. So here, we are keeping this dV as constant. Let us say this is 100, this is 80, this is 60 volts, and this is 40, something like that. So as we are coming closer, so get closer to each other near the point charge. So why they come closer? So let us see. dV is constant, and as we going closer to the charge, the field increases, right? So this increases, field increases, so it should decrease, right? So that's why the distance between the equipotential surfaces decreases as we go closer to the point charge. I hope this concept is clear to you. Now let us see another question. Two uniformly large parallel thin plates having density plus sigma and minus sigma are kept in the xz plane. So let me draw. So this is x-axis, this is y-axis, and this is z-axis. And they are kept in xz plane at a distance d apart. And they are parallel to each other. I think they want to meet in a plane which is parallel to the xz plane, right? Something like this. Let us say there is a infinite sheet which is having surface charge density plus sigma, and there is a negatively charged sheet with surface charge density minus sigma. So that is given to us, and they are placed at a distance d apart. Sketch the equipotential surface due to the electric field between the plates. If the point mass m and charge minus q remains stationary between the plates, what is the magnitude of the and the direction of this field? Okay, right. So what we have given. So we have in the last video we have seen the electric field between two infinite plates with opposite surface charge density is sigma by epsilon naught, right? So at this and this field will be uniform, sigma by epsilon naught. So since field is uniform, so we can say dv, which is equals to minus e dx in this case. Field is constant. So we can say if we move say by a distance dx, there will be a potential change by dv. So you can say the potential gradient will be constant. So if potential gradient is constant, then we can say equipotential surfaces will be equidistant from one another. So we can show it like this. If this distance is say x, then this distance will also be x. So that is the case of a uniform electric field. Now the question is, next part of this question is, if a particle of mass m and charge minus q remains stationary between the plates. The only case when it remains stationary when the gravitational force is being balanced by the electric force. So it means when Fe becomes equals to Fg. Now Fe in this case will be sigma upon epsilon naught, that is the electric field multiplied with the charge, should be equals to mg. So we have to find the magnitude and the direction of the field. So field will be opposite to the, you can say field will be opposite to the gravitational force. A field is this only, right? So from here we can say this is E. Okay, right. So I think they have two separate questions. So let's say this is first part and this is the second part. If there are two separate questions in the second part, we can simply show it like this only. If there is a charged particle, which is there is a gravitational force of mg acting on that charged particle, and there will be a electric force of qa acting in the upward direction. So if we balance these two forces, then the particle will be in equilibrium. So this will be q equals to mg. So E will be mg by q, right? Right. Okay, right. So now the next concept is the relation between electric field and potential. So we have seen one relation, VB minus VA equals to minus integral E dot dr, where integration is happening from A to B. Now here, if electric field is given, we can find the potential difference between the 2 points. But if we have given potential and we want to find the electric field, then we can use this relation. So electric field will be minus del U by del, so not del U, del B by del X, partial derivative, right? I cap minus del B by del Y J cap minus del B by del Z K cap. So we can use this to find the electric field. For example, let me give you a question, give you the illustration. Let us say V is given as X, Y, Z, and del V by del X will be nothing but YZ, and del V by del Y will be XZ, and del V by del Z will be XY, right? So from here we can say the electric field will be minus YZ I cap minus XZ J cap minus XY K cap. Got it? So this by using this formula we can find electric field. Right, so now let us see a question which based on electric field and potential. So two closely spaced equipotential surfaces A and B with potential V and V plus dV, where dV is the change in potential, are kept dl distance apart as shown in the figure. Now these two surfaces are quite close to each other. It is given in the question. Deduce the relation between the electric field and the potential gradient between them. Write the two important conclusions concerning the relation between the electric field and the electric potential. Okay, right. So let's say this point is 2 and this point is 1, and we know this relation. So v2 minus v1 will be minus integral e dot dr, where we are going from 1 to 2, right? And v2 is v plus dv and v1 is v. So minus e dot dr from 1 to 2. So this will be dv minus e dot dr, right? So since these equipotential surfaces are very close to each other, I'm assuming that the distance between them is also very small and the electric field must be having a uniform value. So if that is the case, this we can say it will be, it can be written as integral E dl cos theta, right? Where theta is the angle between the electric field and the dl vector from 1 to 2, and this electric field is having a constant magnitude since the distance between them is given very small. So I can take it out, and cos theta I'm taking out, so this will be integral dl, and this is nothing but this displacement only, right? Minus e cos dl. So this is dv. So from here I can say dv by dl will be minus e cos theta. Now that is the relation between the electric field and the potential gradient. Now to have a maximum value of the potential gradient, cos theta has to be 1. So for maximum dv by dl, cos theta should be equals to 1, and it when the theta is 0 degree. So what we can say, when electric field and the displacement are in the same direction, in that case we'll be having the maximum potential gradient. So potential decreases at the fastest, like gradient will be greatest when we're going in the direction of electric field. So if you look at the second part of the question, write the two important conclusions concerning the relation between the electric field and the electric potential. So first thing we can say, the potential gradient is maximum in the direction of electric field. That decreases, right? So potential decreases by the greatest amount in the direction of electric field. First thing, dv by dt, sorry, dv by dx has greatest magnitude along electric field, right? And second point, what we can say, we can say if we are moving on an equipotential surface, then the work done will be 0. Work done will be 0 if we are moving on an equipotential surface. And what else we can get it from this formula, right? So these are the two conclusions that can be drawn from this formula, right? Okay, now let us see one more example where we have to use this relation VB minus VA is equals to minus integral E dot dr from A to B. So we have given a test charge Q and is moved without acceleration from A to C along the path A to B and then from B to C. In the field, electric field E, calculate the potential difference between A and C. At which point is the electric potential more and why? Right. So we are moving from A to C. If you look at the coordinates, and by the diagram we can it is looking like the electric field is in the right direction. So we can say if I apply this formula, so VC minus VA will be minus E dot dr from A to C. Since electric field, nothing is given in the question whether it is uniform or non-uniform, so I'm assuming but the spacing between the electric field line is not changing, so we can assume it is a uniform electric field. If it is uniform electric field, we can take E out, so it will be E dr, if I take the magnitude, right, cos theta from A to C. If I'm going from A to C directly, right, what is the angle between the electric field and the displacement? It will be, it will be 180, right? So cos 180 is minus 1, so I can write this as E will come out and this will be AC vector with a negative sign, right? Got it? So it will be E times AC vector's magnitude. That will be what? It will be 6 minus 2, 4. So 4E is the potential difference, and our answer comes out to be positive. It means VC is greater than VA. So at which point the potential is more, we can say the potential is more at C, because potential decreases as we go in the direction of electric field. So as we go from C to A, the potential decreases. I hope this question is clear to you. Now the next concept is electric potential energy. Now let us understand what is electric potential energy. So we have a charge Q1, let us say, and let us say it is a fixed charge. And if we bring a charge Q2 from infinity in at some point in space around the charge Q1 from infinity, right? So from infinity we have bring this charge, say at a distance R. So to form this system of two charges, we have to do some work against the field of Q1. So that work will go into increasing the electrostatic potential energy of the system, right? So how we can find that energy? So we can say that energy will be work done by the external agent in bringing the charge from infinity to this particular point, and the potential at this point is Q1 K by R. And if I multiply this, so this is the potential, multiply this with Q2, we will get the potential energy. So do remember this relation. So Q1 Q2 upon 4 pi epsilon naught R12, where R12 is the distance between Q1 and Q2. Now if we have say three charges, if there are three charges Q1, Q2, Q3, in this case how many pairs, first we have to find how many pairs are forming. So in this case there will be three pairs, Q1 Q2, Q2 Q3, and Q3 Q1. Now if we have four charges, how many pairs will be there? So in case of four charges there will be six pairs, right? Say Q1 Q2 Q3 Q4. So there will be Q1 Q2, Q2 Q3, Q3 Q4, Q4 Q1, and Q1 Q3, and Q4 Q2. So how to find the number of pairs? You can apply this formula, so NC2. So it will give you, so if you take two charges in a pair, so how many pairs are possible? NC2. So this is N into N minus 1 by 2. For example, in this case, if I apply this formula, so it will become 3 times 3 minus 1 by 2. So this comes out to be 3. If I apply the same formula in this, it will be 4 times 4 minus 1 by 2. So this comes out to be 6. So once you know the number of pairs, then you can add the energies of those pairs, right? Now let us see the application of that. Calculate the amount of work done to dissociate a system of three charges, 1 microcoulomb, 1 microcoulomb, and minus 4 microcoulomb placed on the vertices of an equilateral triangle. So what we have given? So there are three charges, 1 microcoulomb, 1 microcoulomb, and minus 4 microcoulomb, and they are placed at the vertices of equilateral triangle of side 10 centimeter each. Now we need to find how much work we have to do to dissociate the system, right? So to dissociate means we have to take these charges at infinite separations from each other. So we can say the final potential energy of the system will be 0 because they are at infinite separation. And what is the energy of this system at this instant? So we have to find the number of pairs. So there are three pairs. So just simply find the energy of each pair. So if I consider this as 1, this is 2, this is 3. So U12 plus U23 plus U31. So let us find. Initial potential energy will be K 1 micro square divided by 0.1 plus K 4 micro square divided by 0.1, and it should be negative, right? Because one of the charge is negative. And for 3 and 1, it will be minus K 4 micro square divided by 0.1. So let us simplify this. So K micro square by 0.1 will come out, and we have 1 minus 4 minus 4. So that comes out to be minus 7. So minus 7k micro square divided by 0.1. So let us substitute the value of k. So minus 7 into 9 into 10 raised to power 9 times 10 raised to power minus 12 divided by 0.1. So this will be minus 63 times 10 raised to power minus 2. So minus 0.63 minus 0.63 joules, right? So we know that work done by external agent is nothing but the change in potential energy of the system, because so I'm assuming that we are not changing the kinetic energy. So I've applied work energy theorem. So this will be final minus initial. So U final minus U initial. So U final is 0 minus of minus 0.63 joules. So it will be 0.63 joules. So that is the answer of this question, right? Now let us see one more question. So 2 point charges Q1 and Q2 are separated by a distance 60 centimeter in air. Find at what distance from the first charge Q1 would the electric potential be 0. That I have already covered in one of the question. So that I'm keeping you for you as a homework, right? Also calculate the electric potential energy of the system. So what is the potential energy? So it will be K Q1 Q2 by R. So K is 9 into 10 raised to power 9 and Q1 is given as 10 into 10 raised to power minus 8 and Q2 is minus 2 into 10 raised to power minus 8. So whenever you apply this formula, take charges with proper sign. So potential, because potential energy can be positive, can be negative, and R is the distance between them, which is 0.6. So this will be 0.2. So this will be 3.1. Okay, right. So we have 3 into 10 raised to power 2 minus 8 plus 1. So this comes out to be 3, 10 raised to power minus 8, right? 3 into 10 raised to power minus 5 joules. So that is the answer of this question. Right, so the next concept is the electrostatic potential energy of dipole in uniform electric field. Right, so we have already seen if there is an there is a dipole in external electric field, it will experience a torque, and that torque will be given by P cross E that we have seen in the last video. Now let us find the potential energy, and we always and there, it is customary to take this position when P makes an angle of 90 degree with electric field. We'll take this position, this orientation where the potential energy of the system is 0. So we are assuming this, right? So if we assume potential energy to be 0 in this orientation, and let us say we are bringing or we are slowly rotating this P from this orientation to say this particular orientation when it makes an angle of theta with the electric field, right? Slowly we are rotating this because since the torque is the torque by the electric field will try to rotate this electric dipole in the clockwise direction. So we have to exert an external torque. If this is P and this is electric field, let us say when it is somewhere in between the initial and the final configuration, the angle was alpha between P and E. At this instant, there is a torque by electric field in this direction. So in order to move this electric dipole slowly in this field, we have to exert a torque in the opposite direction. So this is the external torque, right? So we can say the potential energy of the system will be given by okay, right. First we have to find the work done by the external agent. So work done by the external agent will eventually go in the increasing potential energy of the system. So delta U, right? So what is this work done? So this will be, so we can say dW external will be equals to du, and dW external can be written as tau d theta, right? Is it clear? We can write it tau d theta. So in this case, external torque is in counterclockwise direction, and the displacement, angular displacement, is in the clockwise direction. So they are in opposite direction. So work done by external agent is negative of the work done by electric field, right? Is it clear? So work done by electric field will be negative of the work done by the external agent. So we are rotating the electric dipole from 90 degree to theta. So we can say it will be negative of work done by the electric field from 90 to theta, or I can write this as work done by the electric field from theta to 90. I hope it is clear. Theta to 90. So I can write this as work done by the electric field from theta to 90 is equals to du. So we can write this as tau electric field dot d theta, right? So the torque due to the electric field is in the clockwise direction and d theta is in the counterclockwise direction. So it will be minus p e sine theta d theta. So that is du. Now let us integrate this. So we have to integrate this from theta to 90. So it will be minus pe. The integration of sine theta is minus cos theta, and the limit will be from theta to 90 degree. Now this is the change in potential energy of dipole in this field. So it will be u it will be yes, so it will be theta minus u90, right? So let us simplify this. So this negative sign will go away. So we have cos 90 degree minus cos theta times pe. So this will be equals to potential energy when the angle between the dipole and the electric field is theta minus potential energy when the angle is 90 degree. And we know that this value we have taken as 0. So this comes out to be pe 0 minus cos theta. So that will be u theta. So we can say potential energy of an electric dipole placed in electric field will be given by minus pe cos theta, or I can write this as minus p dot e, right? So you can remember this derivation, right? So I hope whatever we have covered, whatever topics we have covered for electric potential and the relation between the electric potential and field are clear to you. Now let us move to the next section, that is the conductors. Now what are conductors? They have large number of free charge carriers and they conduct electricity quite easily. And if I give you some example, you can say metals, human beings and the earth all are conductor because they conduct electricity. Right, so now let us see some important properties of conductors. So first, inside a conductor, electric field is 0. So what does it mean? So when you give some charge to a conductor, then those charges will try to move as far away as possible, and they will adjust themselves in such a way that the field at every point inside the conductor comes out to be 0. So that's why the field inside the conductor is 0. So at the surface of the charged conductor, the electric field must be normal to the surface. Right, so if the electric field inside the conductor is 0, what we can say? By using this formula, VB minus VA equals to minus integral E dot dr. So that is the relation between the potential difference and the electric field from A to B. If electric field is 0, we can say at every point inside the conductor, the potential will be same. So if potential is not changing, right? So we can say the surface of the conductor is also equipotential. If it is equipotential, then we know that electric field is always perpendicular to equipotential surface. So electric field will be normal to the surface of the conductor. So we have a conductor, a charged conductor. At every point on the surface, the electric field will be normal. It will make 90 degree with the surface. Right, so the interior of the conductor can have no excess charge, that I have already explained in the first part. They will try to, there will be a repulsion between them, try to move as far as away possible. So there will be no charge inside the conductor, right? Electric potential is constant throughout. The volume of the conductor has the same value, the potential on the surface is same as the potential at anywhere inside the volume. Yes, and this point we have already explained by using this formula, because electric field is 0, so the potential will be same at every point. And the electric field at the surface of the charged conductor is sigma by epsilon naught. Okay, so this can be shown by using Gauss's law. Let us have a conductor. Let us say there is a conductor, and we want to find the field just outside this conductor. So I'm considering a Gaussian surface, a cylindrical Gaussian surface. Half of this is outside the conductor and remaining half is inside the conductor. So we can say here the field will be 0. Here field is 0. And let us say at this surface, by symmetry, we can say just outside the surface, the field line will be normal to the surface. So electric field will be in this direction. Let us say this area is A, and the area of the conductor which has charge, which lies inside this Gaussian surface, is again A, right? So this area is again A. So if I apply Gauss's law, so we can say E A, I'm only considering the right flat face because the electric field is normal to the surface. So through the curved surface, the flux will be 0. So we are left with only the right face. So EA should be equals to Q enclosed. That will be sigma. Let us say at this location, the surface charge density is sigma. So sigma times the area, that will be the charge enclosed, divided by epsilon naught. So it comes out to be sigma by epsilon naught, right? And it will be normal to the area. Right, so it will be sigma by epsilon naught, normal to the area. Clear? So these are some important properties that you have to keep in your mind. Right, so now let us see different types of molecules. So here we are going to talk about polar molecules and non-polar molecules. What are polar molecules? Which have net electric dipole moment. For example, HCl, water molecule, they have net electric dipole moment. But in non-polar molecule, the center of the positive charge and the center of the negative charge, they coincide each other. So they don't have net magnetic dipole moment. So we call them non-polar molecules. And when we place, say if we have, say a non-polar molecule in external field, let me take an example. So there is a material which is having non-polar molecule. So I'm showing it like this, where the center of the positive and the negative charge, they are coinciding with each other. At present, there is no external field, but if we have some external field, if we exert some external field, then what would happen? Due to this external field, there will be polarization. So this field will exert force on the positive charge in the right direction and on the negative charge in the left direction. So we have a elongation of the molecule, something like this. So where we have positive, where we have negative, like this. Positive, negative, positive, negative, right? For all molecules. Positive, negative, positive, negative, and positive, negative. Now this phenomena is known as the polarization of the dielectric. And due to this polarization, there will be a positive negative charge induced on the left face, and there will be a positive charge induced on the right face. Right? This concept is known as polarization. So we'll study further this effect more in capacitors. Now the next topic is capacitance. Now let us see what is capacitance. So if we have given a conductor, let us this is a conductor, and I have given some charge to this conductor. It has a charge Q, and let us say V is the potential of this conductor. So we'll define a physical quantity capacitance, which is the ratio of these two physical quantities. So capacitance will be defined as Q divided by V. So charge per unit potential. So do remember this formula. And capacitance is measured in farad, that is the SI unit of capacitance. And usually 1 farad is a very big quantity. So the capacitance usually measured in picofarad, microfarad, nanofarad, like this. You should also remember the dimension of that, and you can quite easily calculate the dimension by using dimension analysis by for this particular formula, right? Right. If we have, say, a system of two charges, a system of two conductors, let us say there is a conductor A and there is another conductor B, And let us say this conductor has plus q charge and this conductor has minus q charge, and it is having a potential V1, it has a potential V2. So we'll define capacitance for this system as Q divided by V1 minus V2, where V1 minus V2 is the potential difference between the two conductors and Q is the magnitude of charge on any of these two conductors. So when we have this kind of arrangement, again we are getting a capacitance, again we are getting a capacitor, and this arrangement, or you can say different conductors, we'll call them plates. So here we have two plates, plate A and plate B. Plate A has charge plus Q, plate B has charge minus Q, and the potential difference between them is V1 minus V2. So this is the way how we can represent capacitance for a system of two conductors. Right. So now let us see a question. The given graph shows variation of charge Q versus the potential difference V for two capacitors C1 and C2. Both the capacitors have the same plate separation, but plate area of C2 is greater than that of C1, which line A or B corresponds to C1 and Y. Right, so we haven't done that concept, the formula for parallel plate capacitors. Let us first do that concept, then I'll come back to this question again. Right, so if we have a if I have a spherical conductor and I want to find the capacitance of this spherical conductor. Let us say it has a charge Q and the radius is R. Now, what is the potential of this conductor? So potential of this conductor will be the potential on the surface. So at this particular point A, the potential will be KQ by R. So that is the potential. And we define capacitance as Q by VA, right? Ratio of the charge and the potential. So this comes out to be R by K, so which is 4 pi epsilon naught times R. So if we have a spherical conductor, single spherical conductor, then its potential capacitance will be 4 pi epsilon naught R, where epsilon naught is the permittivity of free space. If I replace vacuum with some other material, then we have to take the permittivity of that particular medium. So do remember, in case of since Earth is a conductor, so if I want to find the capacitance for Earth, we have to substitute value of R, which is 6400 kilometers. And if we calculate for Earth, it comes out to be 711 microfarad. So do remember this value. Right. So, right. So we have discussed what are capacitors, right? Usually we have two plates. Say this is plate 1. This is our first conductor. It is having a charge plus Q. And this is another conductor which is having charge minus Q. Now this arrangement forms a capacitor, and in this arrangement there will be electric field lines from positive plate to the negative plate, and whenever we have electric field there will be energy associated with that electric field. So with the help of the capacitor we can store energy, and that energy can be harnessed instantly if we connect the positive plate with the negative plate. Right. So now let us see the very basic capacitor, parallel plate capacitor. So we have given two parallel plates and we want to find the capacitance between these two parallel plates. So let us say on this plate we have a charge plus Q. On this plate the charge is minus Q, and we know that the right surface of the first plate and the left surface of the right plate, they are acting like an infinite sheet of charge. So we can treat them as an infinite sheet of charge because this area of the plate, we are considering it is very large in comparison to the separation between the plates, right? So if I want to find the field between the plate, it comes out to be sigma by epsilon naught, and that we have derived in the last class, in the last video. So here electric field will be sigma by epsilon naught, where sigma is surface charge density. So here sigma will be charge on the surface divided by the area of the surface. So this comes out to be Q upon A epsilon naught. And what is the potential difference between these two plates? So potential difference will be given by, or you can say the potential gradient is negative of electric field, right? So as we go from left plate to the right plate in the direction of electric field, potential decreases. So we can say the potential difference will be nothing but E times the distance between the plate, and that is D. So we know what is electric field in terms of potential. So if I substitute E as V by D in this equation, we will get V by D as Q upon A epsilon naught, and from here Q by V is epsilon naught A by D, and we know that for a pair of conductors the capacitance is defined as Q divided by the potential difference. So this is the equivalent capacitance of this arrangement. So we have to remember this formula, epsilon naught A by D. Again, this is not in the syllabus, but do remember, if we have a two spherical shells which are concentric to each other, let us the inner radius is A and the outer radius is B, and we have given positive charge to the inner shell, and the outer surface of the outer shell is grounded, and there is a negative charge like this. So it has a negative charge minus Q, and this has a positive charge plus Q. So for this arrangement, the capacitance, there will be electric field line like this. So the capacitance will be given by this formula, that is 4 pi epsilon naught AB upon B minus A. So do remember this, right? But I haven't seen any question from this formula in board exams. If we have a cylindrical capacitors, let us say there are two cylindrical shells. Like this, and let us say on the inner cylinder the charge is plus Q, right? And the length of the cylinder is L, and on the inner surface of the outer cylindrical shell the charge is minus Q. The capacitance of this arrangement will be, so what we have done, we have grounded the outer surface of the outer shell, right? So there is minus Q on the inner surface of the outer shell, and there is plus Q on the outer surface of the inner shell. And the capacitance comes out to be 2 pi epsilon naught L upon ln B by A, where A is the radius of the inner cylinder and B is the radius of the outer cylinder. Okay, right? Now let us see what happens if we insert a dielectric slab between the plates of the parallel plate capacitor. So we have given a parallel plate capacitor, and let us say left plate has a positive charge and the right plate has a negative charge, and there will be electric field from left to right like this. And let us say on the left plate the surface charge density is plus sigma, on the right plate it is minus sigma, and we have already discussed this, like what is the field in between the plates. It will be sigma by epsilon naught. I'm calling this as E naught, right? Now we have now we are inserting a dielectric slab, right? A dielectric material, and in this case the molecules, it is a, you can say, a non-polar molecules. Now what would happen? Now we have placed a dielectric material between in the external field, and due to that field there will be polarization, and we know that due to polarization there will be a negative charge on the left surface of the dielectric. And let me call this as its surface charge density is minus sigma p, and there will be positive charge on the right surface of the dielectric, and this will be plus sigma p. Now if we have plus sigma and minus sigma on the left side, and again, right, so we can say on the left side how much charge we are, how much surface charge we are having, plus sigma minus sigma p. So what is the field due to that charge? Sigma minus sigma p by epsilon naught. Now this is the net field inside the dielectric, and this field, so when we place a dielectric material, the field inside the dielectric will reduce by the factor of dielectric constant of that material. So this will be E naught divided by K, where K is the dielectric constant of dielectric material. So what is E naught? That is sigma upon epsilon naught, right? So if we eliminate epsilon, we can find sigma p, which is sigma 1 minus 1 by k. Now that is the formula for surface charge density on dielectric due to polarization. So you have to remember this formula. And we have, as I have mentioned, the electric field. Okay, right now let us calculate what happens to the capacitance. So Q is epsilon naught A by D times V, right? Where V is the potential difference between the capacitor plates. Now, when we increase or when we insert a dielectric material, the value of epsilon increases. So we can say this capacitance increases, right? If capacitance increases, potential will decrease. So we can say the charge will not change. So we'll be having K epsilon naught A by D times V by K. So that is the case for after insertion of the dielectric. So this is the new capacitance. So capacitance will increase by this factor K, where K is the dielectric constant. Sometimes we'll write it as K, or sometimes we can write this as epsilon R, relative permittivity, dielectric constant or relative permittivity. Okay, so do remember this formula. So K epsilon naught A by D. Right, so now let us see what is the capacitance if a dielectric that we are inserting has a thickness which is less than the distance between the plates. So we have given a parallel plate capacitor. So this plate is having positive charge and this plate is having negative charge, right? That is the charge is Q. Here we have charge minus Q, and we are inserting a dielectric slab which is having dielectric constant K, and the width of this slab is T, and the width between the plate, also distance between the plate is small d, right? So first what you have to do, you have to find the electric field in vacuum and the electric field in the dielectric. So let us, this point is A, this point is B, and even this point at C, the electric field will be same as the electric field at A. So electric field at A and C will be Q upon A epsilon naught, and electric field at B will be Q upon K A epsilon naught, right? Because the field inside the dielectric will reduce by the factor of dielectric constant. Now we want to find the capacitance of this arrangement. So what we're going to do, so I will move from the leftmost plate to the rightmost plate. So this point, let me take this point as 1, this point as 2, this point as 3, this point as 4. So V1 minus V2 plus V2 minus V3 plus V3 minus V4, this should be equals to the charge on the plate divided by the equivalent capacitance, because this is the overall potential difference between the left plate and the right plate. Now V1 minus V2 is nothing but EA times the distance between 1 and 2, that will be if let me take it as X, right? And V2 minus V3 is electric field at B times T, and V3 minus V4 is, let us take it as D minus, it will be D minus X minus T, right? D minus X minus T times the electric field at C, that will be equals to Q by C equivalent. Right, so let us substitute the value. So Q by A epsilon naught times X plus Q by K A epsilon naught times T plus D minus X minus T times Q by A epsilon naught is equals to Q by C equivalent. Now eliminate Q and we can take this epsilon on the other side and A also on the other side. So we have epsilon naught times A divided by C equivalent as X plus T plus T by K, right? D minus X minus T. So this X will get eliminated. So C equivalent comes out to be epsilon naught A divided by T by K plus D minus T. So this formula you can remember. And how to memorize this formula? So in the denominator, if I write it here as 1, so this T by K, so T by K, this T is the width, right, of dielectric, and here we have the dielectric constant. Similarly, if I look at this, D minus T by 1, D minus T is the width of vacuum, right? This plus this, width of the vacuum. And divided by 1, 1 is the dielectric constant of vacuum. So like this we can remember this. Or you can say, if we have multiple slabs of different dielectric constant, in that case it will be epsilon naught A divided by summation of Ti by Ki. Suppose if there are 3 slabs inside between the plates, there will be 3 terms in the denominator. Got it? So do remember this formula. Right, now let us see a question based on the concept that we have studied. So in a parallel plate capacitor with air between the plates, each plate has an area 6 into 10 raised to minus 3 square meter, and the separation between the plate is 3 millimeter. So this is capital A and this is small d. Calculate the capacitance of the capacitor. So here we have to use epsilon naught A by D, right? So this formula we can use to find the capacitance. If this capacitor is connected to 100 volt supply, what would be the charge on each plate? So we know that Q is equals to CV. So we have given potential difference, capacitance we have calculated in the first part, so we can find the charge. Now let us see the third part. So how much charge on the plate be affected if a 3 millimeter thick mica sheet of dielectric constant 6 is inserted between the plate while the voltage supply remains connected? So when the voltage supply remains connected, there will be no change in the potential difference across the capacitor. But the capacitance will change. If capacitance is changing, the charge will also change, because we know that Q is equals to CV. So here voltage is not changing because we have the same battery. So if capacitance changes, Q will change. So we have to find how would the charge on the plate be affected. So first we have to find the capacitance. So for third part, the new capacitance will be epsilon naught A divided by 3 millimeter divided by 6 plus, okay, right, so the entire space is being filled by the mica sheets. Okay, right, so we can directly write the capacitance will increase by K. It will be C times the original capacitance. So if the capacitance is increased by 6 times, the charge will also increase by 6 times, because for the same potential difference, Q is directly proportional to the capacitance. So if this increases by 6 times, charge will also increase by 6 times. Right? So I hope this question is clear to you. Right. So the next question is, when a metallic conductor of thickness T is introduced between the plates, then the capacitance of the parallel plate capacitor is given by, okay, let us see. So we are given parallel plate capacitor, and we have placed a metallic sheet, and we know that for a metallic sheet the dielectric constant is infinite. So if I use this formula, epsilon naught A divided by summation of Ti by Ki, I can say it will be epsilon naught A divided by thickness, that is T. So this thickness is given as T. So T by infinity plus the remaining thickness, remaining space, which will be D minus T. So D minus T divided by 1. So this comes out to be epsilon naught A upon D minus T, because 1 by infinity will tends to 0. Got it? So this you can remember. Right. So now let's see the series and the parallel combination of capacitors. So when we have capacitors in series, when they are connected like this, Let us take an example of two capacitors and there is a battery of EMF E, and this is C1, this is C2. So remember one thing, when we have capacitors in series, they have same charge. So if there is a charge plus Q on this plate, minus Q on this, plus Q on this, minus Q on this, so they have same charge. But the potential difference can be different if they have different capacitance. So if V1 is the potential difference, potential drop across the first capacitor and V2 across the second, V1 plus V2 will be equals to E. And by the definition of capacitance, V1 can be written as Q by C1 and V2 can be written as Q by C2, right? So what we have to do, we want to replace these two capacitors with a single capacitor like this, which is having charge Q, right? This is E. So we need to find the value of Q by E, right? So from here Q by E, or we can say Q by E will be 1 upon 1 by C1 plus 1 by C2. So which is C equivalent, and from here we can say 1 by C equivalent will be 1 by C1 plus 1 by C2. So do remember this formula. Right. So if we have capacitors in parallel, let us see what happens in that case. So if we have capacitors in parallel, so I'm taking a case of two capacitors which are connected with a battery which is having EMF E. This is C1 and this is C2. So when we have two capacitors or three capacitors in parallel, so the potential difference across them will be same, but the charges can be different. So if Q charge is being supplied by the battery, Q1 will go to the to one of the capacitor and Q2 will go to the another capacitor. So Q will be Q1 plus Q2. And by the definition of capacitance, Q1 can be written as C1 times the potential difference. So Q can be written as C1 times E plus C2 times E. So from here Q by E, which is nothing but the capacitance, equivalent capacitance, will be C1 plus C2. So do remember this case. In case of parallel capacitors, we have to add the capacitance. In case of series capacitors, we have to take the reciprocals and add the reciprocal. That will give us the reciprocal of the equivalent capacitors. Okay, and do remember one more formula. If we have two capacitors in series, so for two capacitors in series, the equivalent capacitance will be C1 C2 upon C1 plus C2, right? Okay, now let us see application of the series and the parallel combination. So two identical parallel plate capacitors C1 and C2 have capacitance C each, right? So they have capacitance C each. The area between their plate is now filled with a dielectric as shown. If the two capacitors still have equal capacitance, obtain the relation between dielectrics constant K, K1 and K2. So if you look at the first capacitor, both like C1 and C2, like both the capacitor have the same dimension. Right, so I'm assuming I'm taking area of cross section as A and the distance between the plate is given as D. So C1 will be epsilon naught A times K divided by D. So that is the capacitance of the first capacitor. Now in case of a second capacitor, if you look at the second capacitor, we have two different dielectrics. So this can be shown like this. So we have two capacitors which are parallel to each other. So here we have K1 and here we have K2 dielectric. And these two capacitors are connected in parallel. So if they are connected in parallel, we can simply add their capacitances and we'll get the equivalent capacitance. Now for this capacitor, this length is L by 2, or you can say this will be A by 2, right? Area will be A by 2, because if this length is L, and let me take the width as W, right? So we can say A is nothing but W times L, and here the area in this particular case, if this is W and this is L by 2, so here the area will be W times L by 2. Got it? A by 2, right? So that will be A by 2. So for C2, it will be K1 times epsilon naught A by 2 divided by D plus K2 times epsilon naught A by 2 divided by D. And we have given in the question that C1 and C2 are equal to each other. So this epsilon naught A by D will get cancelled out from these two equations. So we have K equals to K1 by 2 plus K2 by 2. So K1 plus K2 will be 2 times K. So that should be the relation between K1, K2 and K. Now let us see the next question. Can you see this is similar to the question that we have discussed, right? So I'm not going to repeat the same question. So do this question as a homework. Right. A network of 4 capacitors, each of capacitance 15 microfarad, is connected across a battery of 100 volts. As shown in the figure, find the net capacitance and the charge on the capacitor C4. So we have to find the net capacitance. So can you see C1, C2 and C3, they are connected in series and all these capacitors are identical to each other with a capacitance 15 microfarad. So we can say this can be shown like this. So we have a capacitor C4 and we can replace C1, C2, C3 with say C prime. So this is C and here we have a battery of 100 volts. Now what is C prime? So 1 by C prime will be 1 by C plus 1 by C plus 1 by C. So C prime is nothing but C by 3. And C is 15 microfarad divided by 3. So this will become 5 microfarad. So C prime is 5 microfarad and C is 15 microfarad. This is 5 microfarad. Now we have two capacitors which are parallel to each other. In parallel combination, we have to add the capacitance. So this can be shown with a single capacitor with capacitance 20 microfarad. So this will be right. So 20 microfarad is the answer of the first part. Let us say the net capacitance and the charge on capacitor C4. So can you see across C4 the potential difference is nothing but 100 volts. So charge on C4 will be 100 times the capacitance, that is 15 microfarad, right? So this will be 1500 microcoulomb. So that is the answer of this question, right? So let us see one more question. Determine the potential difference across the plates of the capacitor C1 of the network shown in the circuit. So we have given charges. So capacitor C1 and C2 both have same charge. So if I apply, and we have given E2 is greater than E1. So if I apply KVL in counterclockwise direction, so let us move from A point in counterclockwise. So as we move across E2, there will be an increase in potential. So we can write this as E2. Then we are going from a positive plate to a negative plate. So there will be a decrease in potential. So minus Q by C1, right? Then we are going from a positive to the negative plate. So there is a decrease in potential E1. And then we are going from the positive to the negative plate. So there is a decrease in potential minus Q by C2. And we have reached at A. So this should be equals to 0. And we have to find the potential difference across the plate of the capacitor C1. Okay, right. So first let us find the Q. So E2 minus E1 is equals to Q times 1 by C1 plus 1 by C2. And from here we can say it will be E2 minus E1 times C1 C2 upon C1 plus C2. So that is the value of Q, and we have to find the potential difference across the plate of capacitor C1. So potential drop across capacitor C1 will be Q divided by C1. So we have found the value of Q. Now divide this Q by C1. So if I remove C1 and take it on the other side, so this is the potential across C1. Right, now let's see one more question. So the network of four capacitors show each of 12 microfarad capacitance is connected to a 500 volt supply as shown in the figure. Determine the equivalent capacitance of the network. So again, this is similar to the last question that we have discussed, last to last question, where three capacitors are in series. So the same approach we can apply, and again we have to find the charge on each capacitor. Okay, right. So first let us find the equivalent capacitance. Now C1, C2 and C3 are in series. So the equivalent capacitance for these three capacitors will be C by 3. So 12 by 3 microfarad. So that will be 4 microfarad. So we can say 4 microfarad and this is 12 microfarad are connected in parallel. So when we have two capacitors in parallel, so here the C equivalent will be 16 microfarad, right? So we know what is the equivalent capacitance. Now we have to find charge on each capacitor. So what is the charge supplied by the battery? So battery is supplying charge which is C equivalent times the EMF of the battery, that is 500. So this will be 8000 micro coulomb. Clear? 16 times 5 is 80. So 80 times 100 will be 8000. 8000 micro coulomb. And what is the charge on C4? It will be the capacitance, that is 12 microfarad times the potential difference across that. So 500. So this will be 6000 micro coulomb. 6000, right? 5 times 12 is 60. 60 times 100 will be 6000. So if 6000 microcoulomb charge is going to C4 and C1, C2, C3 are in series, and we know that in series combination each capacitor has same charge, right? So now let us see the next concept, and it is the energy stored in a capacitor. So if we have given a parallel plate capacitor, let us say the distance between the plate is D, and let us say initially there is a charge Q and minus Q on left and the right plate. Now, let us say we have taken some dq amount of charge and transferred that dq amount of the charge on the right plate, right? And what is the potential of this capacitor at this instant? So we can say the potential will be Q by C. So how much work that we have done? So work done by the external agent in transferring dq charge from left plate to the right plate will be dq times the potential difference, that will be Q by C. And let us say the final charges on the capacitor is plus Q and minus Q. These are the final charges. So we can say the work done, which is being done by the external agent will get stored in the form of electrostatic potential energy. So we can write this small amount of work done as the increase in the electrostatic potential energy. So it will be Q by C dq. Now if we integrate this and the final charge on the capacitor is capital Q, let us say from 0 to capital Q, it will be 1 by C times Q square by 2. So that will be the potential energy of a capacitor, charged capacitor. Now we know that Q is equals to CV. So we should remember these three important formulas for potential energy. Half CV square. So if we replace CV with Q, so it will be half Q times V. And or we can also write the formula in terms of Q and C. So it will be Q square by 2C. So these three formula you have to remember. Right. Now let us see some of the questions based on that formula. Calculate the potential difference and the energy stored in the capacitor C2 in the circuit shown in the figure. Given potential at A as 90 volts. So potential at A is given as 90, potential at B, since it is grounded, so it will be 0. C1 is 20 microfarad, C2 is 30 microfarad, and C3 is 15 microfarad. And we have to find the potential at, we have to find the energy stored in the capacitor C2. Okay. Now these three capacitors are connected in series. So we can find the equivalent capacitance. So in series combination, 1 by C1 should be equals to, 1 by C equivalent will be equals to 1 by C1 plus 1 by C2 plus 1 by C3. So 1 by micro will come out. So we have 1 by 20 plus 1 by 30 plus 1 by 15. So the LCM will be 60. So 3 plus 2 plus 4. So from here we can find the equivalent capacitance, and that comes out to be 60 by, this will be 9 microfarad. So this will be 20 by 3 microfarad. Now we know the equivalent capacitance. Now let us find the total charge supplied to this combination. So the potential difference, now we have this kind of arrangement. So we have a single capacitor. Here the potential is 90 volt. Here the potential is 0 volt. And capacitance is 20 by 3 microfarad. So we can find, so the V is given as, okay, right. So we can find the charge, right? So charge supplied to the capacitor will be CV. So 20 by 3 microfarad times 90. So this will be 30. So it will be 600 microcoulomb. Now when we have capacitors in series, they have the same charge. So the charge on C2 will be same as 600 microcoulomb. So what is the energy stored in C2? It will be Q square by 2C2. And Q square is 36 into 10 raised to power 4 into 10 raised to power minus 12 divided by 2 into C2, that is 30 microfarad, 10 raised to power minus 6. So this comes out to be 10, this is 10, this will be 12, and this will be 6. So it will be 6 into 10 raised to power 4 minus 12 plus 6 minus 1. So this comes out to be 6 into 10 minus 13. So 10 raised to power minus 3 joules. So it will be 6 millijoules. So the capacitor C2 will be having that much amount of energy, 6 millijoules. Now let's see one more question based on the energy. Two parallel plate capacitor X and Y have the same area of plates and same separation between them. So A and D both are same. If that is same, we can say both have the same capacitance. X has a air between the plate while the Y contains a dielectric constant 4. So it means if this is C, it will be 4 times C, because we know that the capacitance will increase by the factor which is same as the dielectric constant. Calculate the capacitance of each capacitor if equivalent capacitance of the combination is 4 microfarad. So if, since these two capacitors are connected in series, so their equivalent, so C equivalent will be C1 C2 upon C1 plus C2. So that will be 4C square divided by 5C. So that will be 4C by 5. And C equivalent is given as 4 microfarad. So we can find C as 5 microfarad and 4C as 20 microfarad. So that is the answer of first part. Calculate the potential difference between the plates of the capacitor X and Y. So we know that both the capacitors will be having same charge. Let us say it have charge plus Q, here minus Q, plus Q, minus Q. And we know that Q is equals to CV. So charge is same. So potential will be inversely proportional to the capacitance. So we can say Vx by Vy will be, it will, you can say it will be inversely proportional. So it will be C, and here will be having 4C, right? So basically I have applied this. So Vx C should be equals to Vy 4C. So C will get cancelled out. So Vx by Vy will be 4:1, right? So 4:1. So we have to distribute 15 volts in 4:1. So Vx will be 4 by 5 of 15. So that comes out to be 12 volts, and Vy will be 1 by 5 times 15. That comes out to be 3 volts. So that is the answer of second part. Estimate the ratio of electrostatic energy stored in X and Y. So we know that U can be written as half CV square. So Ux will be half C 12 square, and Uy will be half 4C 3 square. Now if I take the ratio Ux by Uy, so that will be half C 144 divided by half 4C 9. So C will get cancelled out, half will cancel out. So this will be so 2, and this will be 72, and this will be 36. and this comes out to be 4. So the answer of third part would be 4:1. Right, let us see one more question. So in the following arrangement of capacitors, the energy stored in 6 microfarad capacitor is E. Find the value of the following. So 6 microfarad capacitor has an energy E. So we can say the potential. So half 6 microfarad V square, that is the potential across 6 microfarad, will be equals to E. So we can say it will be 2E divided by 6 micro root of that. So that will be the potential. Find the value of energy stored in 12 microfarad. So we know since the 6 microfarad and 12 microfarad are in parallel, so 12 microfarad must be having the same potential. So this will be V. So energy stored in 12 microfarad capacitor will be half 12 microfarad times V square, that will be 2E upon 6 microfarad. So this comes out to be 2. So this will be 2E. So the energy stored in 12 microfarad is 2E. Energy stored in 3 microfarad would be what? So what is the charge on both these capacitors? So these capacitors are connected in parallel. So we can find the equivalent capacitance of these two capacitors. So it will be nothing but 18 microfarad. And what is the potential? This is the potential, right? So the charge on 3 microfarad will be same as the sum of the charges on 6 microfarad and 12 microfarad. So Q will be 18 micro times the potential, that is 2E by 6 mu. Now we know the charge on 3 microfarad capacitor, so the potential energy stored in 3 microfarad will be Q square by 2 times 3 microfarad. So this will be 18 micro square times 2E by 6 micro divided by 6 micro. So it comes out to be 18 micro upon 6 micro square times 2E. So this will be 3. So it will be 18E. So the energy stored in 3 microfarad capacitor will be 18E. So this will be 18E. This is 2E. Now the total energy drawn from the battery. Okay, right. So if I want to, so the total energy drawn from the battery will be, so how much charge? So first we have to find the charge supplied by the battery. So Q is 18 micro root 2E by 6y. So total energy drawn by the battery would be work done by the battery, right? Some of this energy, some of the work done by the battery will be dissipated in the form of heat energy, and the remaining work done will be stored in the energy of the capacitor. So work done by the battery will be charge supplied, that will be Q times the EMF, and EMF is not given in this case. So I think in third part they just want to know what is the total energy stored in the capacitors. So if I do that, so here I'm just finding the total energy stored, that will be 2E plus 18E plus E, so which comes out to be 21E. So that should be the answer of this question. Right, so the next concept is the energy density. So it is, energy density is nothing but the energy stored per unit volume in electric field. Right, and it will be given by this formula, half epsilon naught E square, or we can derive this. So let us take a case of a parallel plate capacitor. And we know that in this case, if left plate is positive and right is negative, so the energy is contained only in this region, which has a volume, area of cross section times the distance between the plates. So that it is a cuboid, right? So that is the volume. So energy is half, this is the volume, right? Half C V square, or we can say, yeah, half C V square divided by the volume, which is A times D. That should be the energy density. Okay, so let us simplify this. So U comes out to be half epsilon naught A by D square A V square. So from here I can say A will get cancelled out. So this will be half epsilon naught V by D square. And V by D is nothing but the electric field between the plates. So this will be half epsilon naught E square. Right? So this is the energy density, energy per unit volume. Okay, let us see a question. So obtain the expression for the energy stored per unit volume in a charged parallel plate capacitor. So that we have just seen. The electric field inside a parallel plate capacitor is E. Find the amount of work done in moving a charge Q over a closed rectangular loop A, B, C, D, A. So A, B. So we are going from, we are moving from A along this closed path and we are coming back to the same point. So we know that at A, the potential, if you're coming back to the same position, there will be no change in the potential. So if there is no change, work done will be 0 because work done is given as the charge which we are moving times the potential difference. So VA minus VA, so this comes out to be 0. So 0 is the answer of B part. Right. So the next concept is when we have two charged capacitor and we connect them. So let us understand that. So we have given a capacitor C1 and there is a capacitor C2. And we have charged capacitor C1 with a potential difference V1 and the potential difference V2 for capacitor 2. Now what we're going to do, we will connect the positive plates of both the capacitors together and negative together, right? So when we do that, the charge will move from high potential to positive charge will move from high potential to low potential. And it will move till both the capacitors attain same potential. So first of all, and when they attain same potential, then we can say these two capacitors are connected in parallel because they have the same potential difference. So, so the final charge, let us say, is Q1 and Q2, and the common potential is Vc. So we can say total charge will conserve because we have an isolated system of two capacitors, so the total charge will remain conserved. So total charge will be C1 V1 plus C2 V2, and the equivalent capacitance when both attains the common potential will be C1 plus C2. So if I want to find the common potential, it will be total charge upon equivalent capacitance. So that will be C1 V1 plus C2 V2 divided by C1 plus C2. So that is the common potential, and with this common potential we can find the final charges on the capacitor. Now the second part of this illustration is what is the heat dissipated when we connect these two capacitors. So heat dissipated will be initial electrostatic energy minus final electrostatic energy of the system. So initial will be half C1 V1 square plus half C2 V2 square. So that is the initial electrostatic potential energy, and the final will be half C1 plus C2 Vc square, where Vc is nothing but the common potential. So when we simplify this, we will get half C1 C2 upon C1 plus C2 times V1 minus V2 square. Right? So do remember this formula. So this is for energy dissipation when we connect two capacitors, two charged capacitors together. So there can be some modification in this question. Sometimes it will be given that the positive plate of one capacitor is connected to the negative plate. In that case, you have to take a negative sign here and a positive sign here. Right? Rest of the things will remain same. You will get the answer. Now let us see another type of a question where we have given, let us read this. So when a dielectric slab of dielectric constant K is introduced between the plates of a charged parallel plate capacitor, the charging battery remains connected. So here what we are doing, so we have a capacitor and it's connected with a battery, and this battery will charge this capacitor. So this will be at high potential and this plate will be at low potential. And let us say this is V0. Now what we have done, we have inserted a dielectric slab between the plates of the capacitor, and then we have to find what happens to the potential difference of the capacitor, what happens to the capacitance, what would happen to the charge on the capacitor, and what would happen to the electric field and the electric energy stored in the capacitor. Let us see one by one. So let us see what happens to the potential difference. Since we are not changing the battery, so it is same battery, so there will be no change in the potential difference, so it will remain same, right? We know. Now, as we know, when we insert a dielectric slab, the capacitance will increase by the factor which is same as the dielectric constant. So it will become K times C naught. Now, if I talk about the charge, since charge is C times V, as capacitance has increased by K and potential is same, so we can say it will be 4, or we can say it will be K times C naught times V naught. Is it clear? Where C naught, V naught is the original charge on the capacitor. So it will be K times Q naught. Now, if I talk about electric field is V by D. Since D is not changing, potential is not changing, the electric field will not change. It will remain same. Energy, if I talk about energy, it is half CV square. Since capacitance has increased by K, so the energy will also increased by K. I hope it is clear. Now let us see another type of a problem where we have a charged capacitor. We have given a capacitor which is connected with a battery, and say this is V naught. And now what we have done, we have disconnected the battery. So battery is disconnected, and then what we have done, we have inserted a dielectric slab between the plates. So now we have inserted a slab between the plates. Okay, so in this case, what would happen? So the charge on the capacitor, so there is no path of along with the charge can move. So the charge on this system will remain conserved. So there will be no change in the charge because it is not connected in with any conducting path. And as we and in this case, the capacitance will increase by K, and that we have already studied. And we know that the charge is not changing, and Q is CV. Since capacitance has increased, capacitance has become K times C. To keep charge same, potential should decrease by K, right? So in this case, the potential will decrease by K. And if I talk about the electric field is given by V by D. Since potential has decreased by K, electric field will also decrease by K. If I talk about energy is a half Q square by C. Since charge is conserved, C has increased by K, so energy will decrease by K. So do remember these two important cases. Right, so now let us see another illustration. So initially switch S is closed. So this is closed. And after some time S is left open. So when we close the switch, both the capacitor C1 and C2 will become fully charged by this battery. So we can say initially when switch S is closed, it is charged to 6 volts potential. It is also charged to 6 volts potential. Now after some time S is left open and the dielectric slabs of dielectric constant 3 are inserted to fill completely the space between the plates of the two capacitors. Now what we have done after that, we have opened the switch. Still both the capacitors are charged up to 6 potential difference of 6 volt. Then we have inserted a dielectric in both the capacitors like this, right? And the dielectric constant is given as 3. So how will the charge and potential difference between the plates of the capacitors be affected after the slab are inserted? So let us see. So initially, if I talk about for C1, the charge will be 6 microcoulomb. We have to find the charge and the potential difference, and the potential difference will be 6 volts. Similarly, for C2, it will be 6 microcoulomb and 6 volts. Now after the slab, after we insert the slab between the plates of the capacitor, the capacitance will increase. Let us and then finally for C1, since it is connected with a battery, the first capacitor is connected with the battery, so there will be no change in the potential difference across this capacitor, so it will be 6 volt only. And now the charge will also increase because charge is C times V. C will be and the capacitance here will be K times C1, and which is nothing but 1 microfarad, so 3 microfarad. So capacitance will be 3 microfarad times the voltage, so it will become 18 microcoulomb. So the charge on C1 becomes 18 microcoulomb from 6 microcoulomb. And for C2, since it is not since C2 is not connected with the batteries, so the charge on the capacitor will conserve. So charge will remain 6 microcoulomb, but the potential will decrease to conserve charge. So we know that Q is equal to CV. Since charge is conserved on C2, as capacitance has increased, so potential should decrease. So capacitance has increased by 3, so the potential will decrease by 3. So this will become 6 by 3, so that will be 2 volts. So on C2, the final potential difference will be 2 volts, and the final potential difference across C1 will be 6 volt. So that is the answer, right? Right, so now let us see the next question. A parallel plate capacitor or capacitance C is charged up to a potential V. It is then connected to an uncharged capacitor having the same capacitance. Find out the ratio of the energy stored in the combined system to that stored initially in the single capacitor. Right, so we have connected a charged capacitor with a uncharged capacitor. So it was charged to V and the capacitance was C. Here the voltage was 0 and the capacitance is C. So what is the common potential? So we can apply this formula C1 V1 plus C2 V2 divided by C1 plus C2. Here V2 is 0 and V1 is V. So if we apply, C1 and C2 both are equal. So C times V divided by 2C, so it comes out to be V by 2. So both will have the same potential and that will be equals to V by 2. So what is the final energy stored in both the capacitors after when so usually what happens, the charge will move from low potential to high potential, and when both attains the same potential there will be no flow of charge. After that there will be no flow of charge, and we can say both the capacitors will be in parallel. So in parallel combination, what is the equivalent capacitance? It will be 2C. So the final energy will be half 2C times the final potential difference, that will be V by 2. So this comes out to be CV square by 4, and the potential energy of single capacitor or one capacitor initially in the single capacitor, that will be initial energy will be half C V square, and we have to find the ratio, so that will be C V square by 4 ratio C V square by 2, so that will be 1:2. So that should be the answer of this question. Clear? Right. Now let us see one more question. So find the ratio of the potential difference that must be applied across the parallel and the series combination of C1 and C2 with their capacitance in the ratio 1:2, so that the energy stored in the two cases becomes the same. So we have to find the ratio of the potential difference such that the energy stored in the parallel and the series combination of C1 and C2 will remain same, and we have given that the capacitance are in 1:2. So C1 ratio C2 is 1:2, and we have given energy stored in series is same as energy stored in parallel. So we can say in series combination it will be half equivalent capacitance in series combination times V1 square, and this will be half. Okay, right. So we have given parallel and series. So Okay, right. So this take it as V2, C parallel V1 square. And we want to find V1 by V2. That we have to calculate. And C series will be C1 C2 upon C1 plus C2. So that will be, if I divide this by C2, so this will become C2 square, right? C2. Okay, right. Okay, let me keep it as it is. So half C1 C2 upon C1 plus C2 times V2 square is equals to half C1 plus C2 times V1 square. So we can say V1 by V2 will be equals to, so this half will get cancelled out. V1 by V2 will be C1 C2 upon C1 plus C2 square. Now what we can do, we can divide numerator and denominator by C2 square. So this will become C1 by C2 and C1 by C2 plus 1 square. So this will be 1 by 2 upon 1 by 2 plus 1 square. Basically here we have square, right? So this will become 1 by 2 and then we have 3 by 2 square. So this will be 1 by 2 times 4 by 9. So this will be 2 by 9. So V1 by V2 will be root 2 by 3. So that should be the answer of this question. So here I conclude this chapter. So see you in the next video with current electricity. Thank you.